Hey everyone, so today we are going to talk about buffers, which are chemical mixtures that help resist change in pH. So today you're going to figure out what a buffer is, how we make a buffer, which is two methods, and then we'll do some calculations with buffers as well. So buffers, why are they important? Well, they resist change in pH. It's really good to resist things or changes in pH because even a small amount of acid or a small amount of base can change pH greatly. Your blood is actually a buffer. Your pH range needs to be somewhere between 7.35 and 7.45, so it's slightly basic. Even dropping down to a pH of 7.1 or going up to a pH of 7.8, you could die. So your blood being a buffer is super important to your existence. There's also buffers in some rivers that are surrounded by limestone, which is pretty much calcium carbonate, is also a great buffer. So if you have acid rain or anything like that, the river can resist changes in pH and protect all the wildlife that's living in that river. So let's go ahead and let's get started with this and first talk about what is actually in a buffer. Well, a buffer is a weak acid and its conjugate base. Alright, so it's a weak acid and its conjugate base. No strong acids involved or anything like that. It's just a weak acid and its conjugate base. So an example of this is just HF, which is a weak acid, and its conjugate base, which would just be F minus. Why are these good buffers? Well, if you think about it, right, if we add HCl to a solution, that H plus is what makes it acidic. Well, if we put that H plus in there, that F minus, that conjugate base, is there to eat up that H plus and not cause a change in pH. If we add a OH minus, so if we add a strong base like NaOH and there's an OH minus in there, that weak acid is ready to eat up that OH minus and create a pH change in the basic direction. So that's what these do. The HF eats up the base, the F minus eats up the acid. So that's why buffers are really good at resisting changes in pH. Some other examples of this, we have nitrous acid, right? Not nitric, but nitrous. And then its conjugate base is NO2 minus. You're also going to have other ones. Let's see here what I have written down. You have HOCl, OCl minus. I got another one here. Actually, that's it. That's all I got for my example. So you have HOCl, again, all weak acids and their conjugate base. The problem is that these aren't just lying around free in nature, right? We usually don't see these ions just chilling in a bottle of chemicals, right? These are usually going to be delivered in form of a salt, the conjugate salt. So again, you don't just have F minus floating around. So usually you have it delivered to the system as NaF, right? Then it'll dissociate and then you'll have your F minus. Instead of NO2, it might be sodium nitrite. Instead of OCl minus, it'll be NaOCl. Okay, so that, whenever you see these are just your conjugate bases, okay? Get used to that because a lot of people see these and they're like, what the heck is that? That's really confusing. Okay, that's just how we get our conjugate base into the system. It doesn't have to be Na. Another common one that you'll see is Kf. Alright, because it also dissociates pretty easily. But for the most part, what you see is Na is the spectator ion that helps deliver that conjugate base. Okay? So that is the beginnings to buffers. Let's go ahead and let's see what makes the best buffer. So the best buffers are typically in equal concentrations of that weak acid and that weak conjugate base. So a good example of an awesome buffer would be, say we have 50 milliliters of 1 molar HF and we have 1 molar NaF. Remember, here's our weak acid, and remember that F minus is our conjugate base. It's just being delivered by that Na, right? We have to see it as a conjugate salt. So that is a really good buffer. Equal concentrations of weak acid and our conjugate base. Now I might ask you the question, what is the pH of our solution? And you might be thinking, okay, I have no idea. That's fine, right? You have a 1 molar HF and you have this NaF conjugate base that is kind of throwing things off, right? Well, let's just go back to what we know. If we want pH, we're going to need H+. So if we want to figure out H plus, we need to kind of do some sort of dissociation equation. We got to figure out the dissociation equation pretty much for this buffer. So let's go ahead and let's do that. And one more thing, I'm going to tell you that the Ka for our weak acid is 4 times 10 to the negative 4th. Okay? So let me go ahead and let me show you the dissociation equation for this buffer. So all it is it's our weak acid, and it's just breaking down into H plus, which is what we want to find, and our F minus, which remember is our conjugate base, which is given to us from our 1 molar NaF. And you see Ka, and you might be thinking, hey, don't we need an ice table? No, we don't really need an ice table here, okay? The buffer is already at equilibrium, right? We made the buffer to stay at equilibrium and to resist changes. So it's already at equilibrium. It's only going to change once we start adding those acids and those bases, which we'll talk about later. So here we have our dissociation equation. Our weak acid is going to dissociate into H plus and our conjugate base, which is represented from that NaF. So let's just go ahead and let's do an equilibrium expression if we want to figure out this H plus. We got Ka is going to equal our products over our reactants. So our products are H plus and F minus, and our reactants are HF. And then we're just going to go ahead and plug in those equilibrium concentrations, which I gave you right at the beginning, right? Our HF is 1. And remember, F minus, it's the same as this conjugate salt, which is 1 as well. And then I gave you that Ka right at the beginning, which is 4 times 10 to the negative 4th. And as you can see, this is actually kind of simple because the 1's cancel out, and our H plus actually equals our Ka. So our H plus equals 4 times 10 to the negative 4th. And remember, I'm looking for that pH, so I need to negative log that guy. So let's go ahead and negative log 4 times 10 to the negative 4th. And you should get a pH of 3.4. That is our pH, guys. Okay? So that is a way that you can figure out the pH of a buffer. When they're in equal concentrations like this, whether it's 2 and 2, or 3 and 3, or 0.5 and 0.5, they'll always cancel out, and that Ka will equal that H plus. Here's another thing that you'll start to see, okay? One thing that I'm going to introduce, which is called my pKa. Okay, pKa. Just another way of measuring pH. It's the same as the pH scale, it's just that it varies differently. I think it goes from like negative 10 to 50 instead of 1 to 14 like the pH scale. But a negative pKa or a low pKa is still acidic, and a high pKa is still basic. All right? So when we have equal concentrations like that, when it was like 1 molar of HF and 1 molar of NaF, pKa will equal pH. So right there we had 1 mole HF, 1 mole NaF, they equal each other, and pKa equals pH, but then you're saying, Mr. Dahmer, how does this help us? How do we find pKa anyway? Well, remember, if we want to go from pH to H plus, we just take 10 to the negative pH, right? Well, it's kind of similar for pKa. If we want to go 10 to the negative pKa, that'll give us the Ka. So right at the beginning here, when you saw that the concentrations were equal to one another, you had 1 molar NaF and 1 molar HF, you could have just taken the negative log of Ka, and that would have given you the pKa. Right? So it's kind of similar, right? 10 to the negative pH gives us H plus, 10 to the negative pKa gives us Ka, negative log of Ka gives us pKa, negative log of H plus gives us pH. I know I kind of flipped those, but you get the idea, okay? So whenever you see a buffer solution that has equal concentrations, just take that negative log of the pKa, and it'll give you the pH right off the bat. Or you could go ahead and write that equilibrium expression like I did and just go through the whole thing like I did right here at the beginning. All right, so what is important, or why is it important to know that pKa? We'll talk about that next. All right, so here's an example of why it's good to know about pKa. So here I've given you 3 buffer solutions. They're all the weak acid and their conjugate base, and they're all in equal concentrations. So here we should know that since they're in equal concentrations, our pKa is going to equal our pH. So let's go ahead and let's fill in these boxes here. I've left some boxes blank in order for us to solve for them just by knowing simply that our concentrations are equal and we have either one of those 3, either Ka, pKa, or pH. So let's go ahead and let's look at this. So I'm looking at the first one. They're in equal concentrations. I have a pKa. Remember, in equal concentrations, the pKa equals the pH. So those are both 3.17. I still need to figure out that Ka. Well, remember that Ka is going to equal 10 to the negative pKa. Right? So we have pKa, which is 3.17. So 10 to the negative 3.17 pKa. I said 10 to the, I did a syntax error, 10 to the negative 3.17 pKa will give us a Ka. Let's go with 6.8 times 10 to the negative 4th. Okay, so that's one helpful thing. And the second one, both equal, right? So Ka or pKa and pH should equal one another. They didn't give us any of those, but they did give us Ka. Well, remember that the negative log of Ka will give us pKa. So let's just take that negative log of our Ka there instead, which is 2.9 times 10 to the negative 8th, and that will give us our pKa of 7.54. And of course, since they're in equal concentrations, that is also our pH. Again, 1 molar of HF, 1 molar of NaF. We kind of did this already, right? We know the pH, so the pKa is going to be that. And then if we just take 10 to the negative pKa, we'll get our Ka. I think it was 4 times 10 to the negative 4. All right, so that's just some good things to know. Again, only if they're in equal concentrations. Well, what if they're not in equal concentrations, right? What if we got different non-equal concentrations for HF and NaF? Well, just revert back to your equilibrium expression like we did earlier. So, again, if we're looking at HF and it dissociates into H plus in the conjugate base, which remember is NaF, and say that we just have 1.2 molar HF, and this time we have 0.8 molar NaF, and we want to calculate the pH of this one. Now that they're in different concentrations, let's calculate the pH. Well, let's just kind of do a little bit of a guess here at the beginning using our knowledge, right? If we have a stronger concentration of the weak acid than the conjugate base, do you think the pH is going to go up or down from the original pH here of 3.4? I think it's going to go down, right? It's going to be more acidic since we got 1.2, a stronger concentration of this weak acid. Acids, when they increase in strength, go down in pH. So this should have a lower pH. Well, let's just figure that out, right? We got to do Ka equals products over reactants as usual. We know that our Ka is 4 times 10 to the negative 4th. We know our F minus is now 0.8 because NaF and F minus are the same. And we now know our HF is 1.2. I expect you know how to do the algebra for here on out. So 4 times 10 to the negative 4th times 1.2 divided by 0.8 gives us an H plus of 6 times 10 to the negative 4th. We negative log that 6 times 10 to the negative 4th to get our pH, which is going to be 3.22. Hey, we were right. that's going to decrease the pH. What if we flip these, right? What if we just decided to go more NaF? So we now have 0.8 HF and 1.2 molar NaF. Well, if we increase the concentration of the conjugate base, you'd probably expect the pH to go up, right? Well, let's figure this out. Instead of going through all the motions here again, let's just plug in our concentrations. Remember, this is now F minus, this is now HF. I'll keep that pH there for last time so that we can look at it later. But we got 4 second e to the negative fourth times 0.8 divided by 1.2. Our new H plus is 2.67 times 10 to the negative fourth. Right? I'm going to negative log that down here. 2.67 times 10 to the negative fourth. And now our new pH, when we flipped the concentrations and gave us a higher concentration of our conjugate base, is now 3.57 pH. Alright, this is just a good conceptual thing to know. They will flip these on you and ask you conceptually on the AP exam, if we have a higher concentration of our conjugate base, where would you expect to be in a higher concentration, the F minus or the HF? You're going to say F minus, right? Because the higher concentration, you'd expect the pH to be higher as well. So the concept pretty much from this, of these concentrations not being equal, is that they want you to come away with this simplification. And that's that if HA equals A minus, so our weak acid equals our conjugate base, pH is going to equal pKa. If our HA is greater than our conjugate base, which is in our first example, our pH is obviously going to be greater than our pKa, right? The pKa is never going to change, but the pH can. All right? And then, this is flipped. The pH is going to be less than the pKa, right? Because the lower the pH, the more acidic it is. Sorry about that. And then the opposite, right? If the conjugate base is in a higher concentration, then the pH is going to be greater than the pKa. All right, so just be aware of that. They like to ask you questions like that. The pKa, unlike the pH, never changes, right? Ka is our acid dissociation. It tells us how much the acid is going to break down. Well, the pKa kind of does that as well. So it's going to stay the same, but our pH definitely can change based on our changes in concentration. So again, we had more of our weak acid, pH went down, it was lower than our pKa. We added more conjugate base, our pH was higher than our pKa, more basic. Let's move on to our next buffers topic. So here is the next important thing we're talking about, which is how to prepare a buffer. Method 1 we already kind of talked about. It's having equal parts of that weak acid and that conjugate base, which is delivered as a salt, right? So we mix a weak acid with this conjugate base. An example of this is that we have 500 milliliters of 2 molar HF, we have 500 milliliters of 2 molar NaF. Hey, they're the same concentration, same amount. And then when we mix them together, right, remember their volume is additive. So now it's 1,000 milliliters of 1 molar HF and 1 molar NaF. So be aware of that. And you could do a calculation for this if you want to, if this part right here is kind of confusing, right? We can figure out the moles of each of these guys, right? 0.5 liters times 2 molars is 1 mole of HF. 0.5 liters times 2 molar NaF, we have 1 mole of NaF. And then remember we added those volumes together. So now instead of 1 mole of HF being in 0.5 liters, now it's in 1 liter. Same with this NaF. So that's why they're both in a concentration of 1 molar. So remember that when you're adding those weak acids and that conjugate base together, you got to remember that their volumes are additive. So that's why we ended up with kind of double the concentration, because we know when we add it to the same amount of volume, it's going to cut that concentration in half. So this is the first one. Again, say we got weak acid, conjugate base, we add them together. But here's the thing, what if you don't have any of that conjugate base like NaF just lying around? Well, you could always start with a weak acid and then add strong base. This is an important one that they like to ask you about in the AP exam, especially on the multiple choice. It says we start with a weak acid and then we add a strong base until half of the weak acid is neutralized. So we're looking at moles here, right? Remember that HF, when it dissociates into H plus and F minus. And we want the same amount of HF and F minus, the weak acid and the conjugate base. That makes a great buffer. Well, think about it. If you happen to have 1 molar HF and then you eat up half of that, right? Well, remember, if you eat up half of that with a strong base, half of it's going to remain HF, 0.5 of it's going to remain HF, and then the other half of it is going to turn into F minus. So that's what the strong base is doing. It's turning half of that weak acid essentially into F minus, half of it into the conjugate base. So that's why we add that strong base. So an example of that, I'll leave that down there, is we have 100 milliliters of 2 molar HF, and we just add 100 milliliters of 1 molar, not HF, NaOH, strong base. And that ends up giving us 200 milliliters of 0.5 molar HF and 0.5 molar F minus. Let's do a similar calculation to what we did over here, right? So when we started, you have 100 milliliters of 2 molar, right? So that ends up being 0.1 times 2 equals, so we have 0.2 moles of HF. And then we do 0.1 moles, or 0.1 liters times 1 molar. That will give us 0.1 moles of NaOH, which really is the OH minus that we care about. Well, remember that base is going to react with that acid, and it's going to be 0.1 moles of OH is going to react with only 0.1 moles of that HF. So at the end of it all, we only will have 0.1 moles of HF, and that 0.1 moles of HF is going to get turned into 0.1 moles of F minus, as I explained earlier. And remember, the volumes are additive, so it was over 0.2 liters for both of them. That equals 0.5 molar F minus, 0.5 molar HF. So remember that we could add equal amounts of the conjugate, or the weak acid and the conjugate base, or we could have weak acid and just neutralize half of it, okay? Another thing you could have done here at the beginning is that you could have just done 50 milliliters, say, of 2 molar NaOH, right? It would have ate up the same amount of moles. You would have had 0.1 moles of NaOH, still would have had 2.2 moles of HF. It still would have worked, okay? So you just kind of have to work with what they give you. Let's go ahead and look at a calculation involving these buffers. So no calculation yet. I forgot that. We got to go over how long is a buffer effective. Typically, if the pKa equals pH, the buffer is effective for a pH of plus or minus 1. Okay, so let me explain that. And when we were talking about our 1 molar hydrofluoric acid and our 1 molar sodium fluoride conjugate base, right? We said that it had a pKa equal to 3.40, which is also its pH. So that means its buffering range is equivalent or is effective until 2.40 pH and 4.4 pH. So pretty much it can resist pHs in that range. If you start adding too much base or too much acid where it gets below 2.4 pH, or if you add too much base where it gets above 4.4, it's not effective anymore, and that pH is going to skyrocket or it's going to go way down. So that's a good thing to know when you're making a buffer. You want to make sure that it's in a range plus or minus 1, right? So if I want a buffer for my blood, I want to make a buffer that's somewhere in between 7.3 and 7.4. And I want to know that I can't add anything greater to that buffer that will affect it a pH of plus or minus 1. Let's go ahead and let's talk about these net ionic equations for these buffers as well. That's also a question they love to ask you on the AP exam. So something they might ask you is that, the question is, what happens when a strong base or strong acid is added to a buffer? So what happens when a strong acid or strong base is added to a buffer? Alright, so let's look at an example of this. Alright, suppose we add HCl to a buffer of our famous buffer, HF and NaF. Write the net ionic equation. Alright? Write the net ionic equation. That's not a question, it's a command. Why am I putting a question mark in there? So anyway, they like to ask you this on the AP exam, and they just want to ask you what the heck's going on in this buffer. Well, remember, a buffer helps eat up H+, or it helps eat up OH-. Well, in this case, we're adding H+, so we're expecting to eat up H+. Well, when we add H+, okay, to the equation, what's going to be reacting with this H+? Is it going to be our weak acid or our conjugate base? It's going to be our conjugate base. So, again, we don't care about Na, it's a spectator ion. All right, it just is chilling there, just delivering the F- into the solution, and then it's going to create some of that weak acid. So that is what is happening if we added HCl. That H+ from the HCl is coming in, that conjugate base from our NaF is eating up that guy and turning it into a weak acid. It's trying to help not change that pH whatsoever. What if we added NaOH? This is part 2. What if we add NaOH? Well, remember that OH is just trying to react with whatever's in the buffer, right? So that OH- has come in, and what's it going to react with? It's not going to react with the conjugate base, that's a F-, right? It's going to react with that weak acid, which is HF. And here you might be wondering, okay, OH- and HF don't really go together. And you're right, right? But what's going to happen when this OH reacts with this HF? Remember, the conjugate base and the H+ reacted to make the weak acid. So now the weak acid and the base is probably going to react to make the conjugate base, right? It's going the opposite direction. So we're definitely going to have F- as one of our ions on the right side. Well, that leaves us with OH and H left over. Well, what do they make? They just make water. Okay, so that is the net ionic equation for both of those guys. They love to ask you that. They want you to know what's actually going on in a buffer. Well, that acid that's getting added is getting eaten up by that conjugate base to make it a weak acid. That strong base is getting eaten up by that weak acid to make it a conjugate base, and you got some water chilling over there as well. All right, so that is what happens when we have net ionic equations with buffers. All right, here's a lot. I don't need you to write this down. If you want to, go ahead. But I just kind of want to explain what's happening here with the buffer and how powerful they are. All right, so how does a buffer resist change in pH? Well, here at the beginning, we're going to navigate all this. Let's just say I have 1 liter of 1 molar HF and 1 liter of 1 molar NaF. This is a good buffer, right? They're in equal concentrations. And I've just simplified them that we have 1 mole of HF and 1 mole of F-. And we have established that this buffer has a pH of 3.4. Well, what if I go ahead and I add 1 milliliter of 10 molar HCl? That's a pretty strong acid, 10 molar. I just add a milliliter of it, so that ends up being just 0.01 molar of H+. Well, remember that H+ is going to get eaten up by that F- and turned into our weak acid. So what happens is that when that 0.01 mole of H+ reacts with that buffer, we end up eating up our 0.99 moles of F- and our 1.01 mole of HF. Well, if we go down here and we look at our Ka expression of H+ and F- over HNO2, and we plug in our Ka and our new molar concentrations, we end up with an H plus of 4.1 times 10 to the negative fourth, which if we negative log that gives us a pH of 3.39. That's a pretty small change in pH. Okay, we just added 0.01 moles of H plus, and that gave us a pH of 3.39. Let's go ahead and let's say we don't add this to a buffer. Let's say that we just go ahead and we add the same amount, but this time, instead of adding that 1 milliliter of 10 molar HCl to a buffer, we added to just 1 liter of H2O, right? We added to 1 liter of water, which has a pH of 7, right? Water is neutral, okay? Well, we added that 0.01 moles of H plus. Well, wait a second, there's nothing there to eat up that H plus, right? So that H plus is just sitting there in that water with a H plus concentration of 0.01. Okay? Well, if we negative log that 0.01, we now have a pH of 2. So that is crazy. The buffer, when I put that 1 milliliter of HCl in there, it only changed it by 0.01 pH. But when I put it into water, just pure water, it changed it by a whole whopping 5 pH. So that is the strength of buffers. Okay, that's how important buffers can be. If we didn't have buffers, we'd just be a acidic basic mess pretty much our whole lives, okay? So there is that. Now, let's get into the calculations. All right, guys, time for buffer calculations. And the main thing you can do is that you could either use our equilibrium expression or you could use this new equation called the Henderson-Hasselbach equation. Okay, so when you see buffers, you're thinking, okay, I could use the Henderson-Hasselbach equation. It's a possibility, okay? Not named after our own Mr. Henderson. That would have been cool, though. So anyway, what is the Henderson-Hasselbach equation? It's just pretty much used to calculate the pH of a buffer. So what it is it's pH equals pKa plus log of, let's put that in regular brackets, A minus over H. So it's essentially our concentration of our conjugate base over the concentration of our weak acid. So our NaF over our HF, or our NaNO2 over our HNO2, or our NaOCl over our HOCl. Any weak acid conjugate base combination. So what this does is that it just helps you calculate the pH of a buffer if you know pKa or Ka and you know those concentrations. Or you could just use what we've always been using, which is our equilibrium expression. So you could also just use Ka equals H plus over A minus over HA. So concentration of weak acid, concentration of conjugate base, you have the Ka. You could just solve for H plus and then negative log that to get pH. You can use either one. You could use method 1 or method 2. These are both on the AP chemistry equation sheet. So whichever one you're more comfortable with, go ahead and use either one of those, okay? So I'm going to go ahead and I'm going to put these up on top here. And then we'll do a few calculations and we'll be done, okay? So there's option 1, Henderson-Hasselbach, or Hasselbeck, or whatever, I don't know. I'm sorry. I should know. But I don't. I'll say Hasselbach. Henderson-Hasselbach. Alright. I've killed enough time. Alright, so let's look at our first example. A buffer contains 1.2 molar HNO2 and 0.8 molar NaNO2, so nitrous acid and sodium nitrite. Sorry. What is the pH of the buffer? And I'm going to give you the Ka. Let's just say it's 4 times 10 to the negative 4. Okay, even though we've been using that for HF. So, again, a buffer and wants the pH, go ahead and feel free to use number 1 or number 2. Let's go ahead and use both just to kind of see what's going on here. So we want the pH is what we're looking for in the Henderson-Hasselbach equation, but we need pKa. But right now they have only given us Ka. Well, remember that the negative log of Ka equals pKa. So let's just go ahead and negative log that Ka, which I'm pretty sure it's 3.4, but I'm just going to do it anyway just to make sure. Yeah, it's 3.4. All right, so now our pKa is 3.4 plus log of concentration of our conjugate base, which in this case is NaNO2, so it's 0.8. And then concentration of our weak acid, which in this case is 1.2. All right, easy peasy, right? 3.4 plus log of 0.8 divided by 1.2 gives me a new pH of 3.22. One way to do it. Let's do it with number 2 as well. We know Ka, which is 4 times 10 to the negative 4th. We don't know H+, that will help us get our pH. We do know A-, right? That's our 0.8. That's our conjugate base, is that little salt that they gave us. And I know the concentration of my weak acid, which is 1.2. Let's solve for H+. 4 times e to the negative 4th times 1.2 divided by 0.8. So now I get a H+. I know we've done this before. Of 6 times 10 to the negative 4th. We negative log that. And we get a pH of 3.22. I'm guessing. Yep, 3.22. All right, so same thing. Doesn't matter. You could use either one, whatever one you're comfortable with. Just know that those are used for buffers. All right, let's go ahead and let's look at another example. All right, our last example. A buffer solution contains a mixture of HC2H3O2, which is acetic acid, and NaC2H3O2, which is sodium acetate, with a pH of 5. If the concentration of acetic acid is 2 molarity, what is the concentration of the acetate ion in the buffer or the conjugate base? Well, once again, we have a buffer solution here. We're thinking we're probably going to be using Henderson-Hasselbach or our equilibrium expression. It wants the concentration of acetate, which is our A- in our equations. So let's go ahead and let's plug in what we know. Did they give us a Ka? They did give us a Ka. Of course they did. Because how would we have solved it without our beloved Ka? Alright, so let's go ahead and let's solve this by using Henderson-Hasselbach first. Okay? 1, pH we know is 5. That's what they gave us, right? pKa we don't know, but remember they gave us Ka. We could just negative log the Ka to get pKa. So negative log 1.8 second e to the negative 5th is 4.74 plus log. Remember, we don't have A-. That's what we're looking for, right? We're looking for that acetate ion, that conjugate base. So A- over HA, which they told us was 2. Let's simplify this as much as possible, right? Let's combine these like terms. So let's take 5 minus 4.74 to both sides. And we get 0.26 equals log of A- over 2. We got to get rid of that log. Remember the inverse of log. You could just look on your calculator if you want to. Is 10 to the. So to get rid of that log, we'll do 10 to the log and 10 to the 0.26. 10 to the 0.26 is, I'm going to erase this one. 10 to the 0.26 is 1.82, which equals A- over 2. Well, just times by 2 to both sides to get the concentration of that A-, which is now 3.64 molarity. Remember that A- is our conjugate base. So there's it using Henderson-Hasselbach. Well, it wouldn't be right if I didn't show you the other way either. So let's go ahead and let's do it the other way. Ka is 1.8 times 10 to the negative fifth. H plus, how can I get H plus? Well, they gave us the pH, right? Remember that 10 to the negative pH equals H plus, so let's just take 10 to the negative 5 to give us our H plus of 1 times 10 to the negative fifth. I don't know A minus, that's what I'm looking for. And my concentration of my weak acid is 2. All right, here we go. 1.8 second e to the negative fifth times 2 divided by 1 second e to the negative fifth gives me a concentration of A minus of 3.6. Same thing either way. All right, so that is buffers. Remember, make sure you know how to make a buffer, whether it be method 1 or method 2. Make sure you know what a buffer does, how it eats up OH minus from the weak acid and it eats up H plus from that conjugate base. And make sure you know how to do these calculations, whether it be Henderson-Hasselbach or just our equilibrium expression. It is up to you. That is it. Have yourselves a great day.